que ligar. Já tá. Não, tá assim. Tá verdinho aqui. Lá. Batendo aqui. Tá. Será que tá? Bem fraquinho, né? Foi. Ligar mexendo nisso aqui. Testando. Agora tá. Agora eu vou aumentar. Olá. Isso. Eu acho que agora tá indo. Tá indo. Uhum. Tá.
Boa tarde a todos. É um prazer receber aqui o Dr. Pedro Rossetto. Muito obrigada por aceitar o convite. Ele é da Escola de Artes, Ciências e Humanidades da Universidade de São Paulo, fazendo atualmente um pós-doutorado, juntamente com o professor Diego Falseta Gonçalves, e também é colaborador do Grupo de Astrofísica de Alta Energia e Plasma do IAG. Realizou também pós-doutorado na Universidade de Melbourne em 2023, concluiu a graduação e mestrado em Física na Universidade de Brasília e fez o doutorado na Universidade de Otago, na Nova Zelândia. Seus interesses de pesquisa incluem MHD relativística e clássica, aceleração de partículas, ondas gravitacionais e dinâmica caótica, sobre o que ele vai falar um pouquinho hoje. Muito obrigada, o espaço é todo seu.
Hello, everyone. I will do the talk in English. I just wanted to ask again, is there any geophysicist in the audience? No? No? Okay. Maybe I won't embarrass myself. Good. Okay. So I will talk about continuous gravitational waves from neutron star magnetic mountains. Very big title, could be even bigger. This is a project that I did for my PhD. Let me put some time here so I don't run out of time. Yeah, and thank you for the invitation to present here. So, quick outline of my talk. I will give some background and motivation. Then I will talk about magnetically confined mountains on neutron stars. And then I will go to continuous gravitational waves. But before all that, I just wanted to do a quick who is me. So I'm Pedro, and I'm very proud from being from Brasilia, the best city in the world. This is our airplane city, and this is the same place in the city 6 months apart, more or less, in our 2 seasons, dry and rain. So I was born and raised in Brasilia. In 2013, I joined for my bachelor's in Brasilia, the University of Brasilia. And then I did a short-term study abroad in Canada with Professor Martin Duncan on planet formation at Queen's University. Then I went back to Brasilia and I did my master's degree there. Professor Sergio Lhoa on PP wave spacetime, so already starting some GR stuff. And then I went to New Zealand. My talk had a soundtrack. You can imagine what would be playing now. And there I did my PhD during the pandemic with Professor Jorgo Fraundiner and co-supervised by Andrew Melatos in Melbourne on the topic of this talk, magnetically confined mountains and neutron stars, the University of Otago. Then I went to Australia, and I did a postdoc at the University of Melbourne. I did some extensions of my PhD work there with Professor Andrew Melatos. All right. Of course, now I'm here in São Paulo, and so I joined April this year, and I'm doing my postdoc, and I'm working closely with Professor Diego Falseta Gonçalves, and I'm collaborating with GAPAI, the group of Professor Elizabeth. Okay, now let's go to the talk. Background and motivation. So neutron stars are sometimes found in these binary systems, like low mass X-ray binaries. And this kind of systems give us 2 interesting problems. The first one, they are naive problems, but they are problems. The first one is, why do the neutron stars inside the systems do not spin faster than what we observe? And the second one is, why the magnetic field values that we observe of the neutron star are lower than compared to the isolated isolated neutron stars. So this first problem is, if you do a simple calculation of how much mass is falling to the neutron star, how much angular momentum the neutron star is receiving, you would see that they should spin up to 1,000 hertz and break apart, but that's not what happens. And yeah, the magnetic field is low. So here are some experimental data, not that I do anything with those, but just some motivation. And so for the problem of the spin, you should have some mechanisms to lose angular momentum. And we know that maybe the main mechanism is electromagnetic radiation, wind emission. But one of the possibilities, if you have a magnetic axis that is not aligned with the rotation axis and you have some kind of deformation, you can generate gravitational waves and emit angular momentum that way. By the way, if anyone have questions, I'm happy to take them as I talk. Well, otherwise, you can ask at the end. So yeah, so for gravitational waves, you need a time-varying quadrupole moment. And for that, that's what we call mountains. So these deformations is what the literature calls mountains. There are two main categories of mountains. There are the elastic mountains and magnetic mountains. The elastic mountains are deformation from elasticity of the star. And so they are limited by the strain on the crust. And yeah, and like rotational effects or gradients, thermal gradients can generate this kind of deformations. Or there are magnetic mountains that are present both in isolated neutron stars and binary neutron stars. And in isolated neutron stars, if you have a magnetic field and a ball of fluid, because the magnetic field cannot be spherically symmetric, right? There is no monopole. You are going to have some deviation from spherical symmetry of the star. This is more relevant for magnetars who have very strong magnetic fields, but my topic is neutron stars in binary systems. So this is an awesome animation that the people in Australia did. Let's see if it works. It's a bit glitchy, but yeah, anyways. You have a low mass companion that is losing mass through overflow of the Rossetto lobe. And this mass is falling to the neutron star, creating this accretion disk and emitting this ridiculously disproportional gravitational waves here in the animation. Of course, gravitational waves are tiny. So yeah, so I'm going to talk specifically about magnetically confined mountains. So what happens? I try to give like a qualitative picture. So you have the accretion disk and the neutron star with the magnetic field. And at this inner edge of the accretion disk in the magnetosphere, the plasma is going to start following the magnetic field lines. Up here is gravity dominated, but inside the magnetic field dominates the dynamics. So this matter starts to accrete and follow the magnetic field lines and start accrete in the pole. And this matter that is accreting is a plasma, and when it starts to pile up, it starts to deform the magnetic field. So a simple idea is that this matter is going to start accumulate on the poles. Maybe I should be pointing to okay. This matter is started to accumulate to the pole. Gravity is going to do what it does and try to make this spherical, but because there is magnetic field frozen into the plasma, when the matter starts to move towards the equator, the magnetic fields are going to react to it, the magnetic tension, and so on. Yeah, and hopefully this display between gravity trying to make the matter goes to the equator and the magnetic field trying to hold up the initial configuration, maybe this is going to create an equilibrium state for us, for our gravitational waves. Yeah, so this model, qualitative model that I explained, have been studying the Newtonian literature for a while now. There are papers from 1981, but the most important paper here was 2004 by Andrew and one of his PhD students. And I will get to what I've done, but for now I will explain what they did before. So what happens? You get the equations from first principle, which is the equations of magnetohydrodynamics. For who don't study plasma, this is the continuity and the fluid equations plus Maxwell's equations, Ohm's law, the Poisson equation for the gravitational potential. But then you can make some relevant approximations, our beloved spherical cows. The first approximation is that the gravity is generated by the neutron star and not by the mountain. Normally, the amount that is accreted is much smaller than the mass of the neutron star. So you can say that you are in this background, like a Newtonian potential. And you consider this system to be axisymmetric with respect to the magnetic axis. This is very important. I always get this question. It's not axisymmetric with respect to the rotation axis. This way, there wouldn't be gravitational waves. It is axisymmetric with respect to the magnetic axis. So, and you assume that the field is totally poloidal. So the magnetic field can be written this way. So phi here is the spherical coordinates phi, and psi, this is the important guy. So this is a scalar potential that generates B. It's in the normal vector potential of the magnetic field, it is the phi component. And why can we generate this magnetic field from a scalar and not a vector potential? Is because of this axisymmetry and poloidal condition. All right, then you can treat the system in ideal MHD, meaning that the fluid is a perfect conductor, and you can say that the system evolves in quasi-static steps of magnetostatic equilibrium. What this means is that the accretion dynamics is much longer than the characteristic time scales of the problem, the alpha van time scale, and then you can model this in equilibrium. Right. And what happens when you put all these conditions into your first principle equations after you run the math, and you get this equation here. It's the Grad-Shafronov equation, and this, so the Grad-Shafronov equation is for this function psi. Remember, psi is the important guy here. It's what generates the magnetic field. And in spherical coordinates, this is the Grad-Shafronov operator, which have all these components. If you are very familiar with the Laplace operator, you might be thinking that this is the Laplace. It's not. This sign and this sign are kind of swapped. But anyways, and you have this right-hand side here, which is a source term, and defined by this function f. And this function f is given by this beautiful relationship here. So if you know a bit about PDEs, you can imagine the headache that this is, because this is a elliptical equation, but with an integral condition that depends on the solution itself. So it's nonlinear equation, a bit hard. By the way, before this work that I'm summarizing here, people used to just guess this f of psi, of like, let's do something like this. But this way, if you do this way, you have it self-consistently. Okay, and what results do they get? They got pretty much this result here that I'm showing. In dashed lines, you have the initial dipole of the neutron star, and in solid lines is the final magnetic field after the mountain has been accreted. So you can see that what happens is that the mountain deforms the magnetic field, and I'm not showing the density, but I'll show later. But and the mountain spreads to the equator, tries to spread to the equator. So you get this, and you call it magnetic tutu, and the Brazilian tutu, which is feijão, it's the bailarina tutu. Yeah, and the matter spreads towards the equator, dragging the magnetic field with it. Okay, and how does this relate to the observational problems that I was discussing before? Well, we have two nice results. First one is that the magnetic dipole moment decreases. So you see a decrease in the magnetic dipole moment, and you see an increase in mass ellipticity or quadrupole. This means that maybe we can try to, we are explaining the small magnetic field values by this process, which is called magnetic burial. And maybe the ellipticity here is helping radiate angular momentum away from gravitational waves. And as I said, this problem has been studied in the Newtonian literature, and many improvements have been made on this basic model. One very important improvement was the equation of state. So Prima in 2011 showed more realistic equations of state, and that reduces the ellipticity by quite a lot, 3 orders of magnitude. And by the way, when I say equation of state, I also get this question a lot. People ask, oh, neutron star equation of state? No, it's mountain equation of state. We are modeling the mountain itself, not the neutron star. But you can do a kind of a mix where the mountain sinks to the neutron star, and there is some matter mixing there. But anyways, you can also ask about the stability of these mountains. You have these MHD configurations that are very distorted. Plasma people knows that these configurations are very unstable. So actually, Andrew was thinking, this is nothing, it's just an unstable configuration. But when you actually run the MHD codes in it, you get stability, and this is mainly due to the line tying boundary conditions at the surface of the neutron star. There are some people who study crustal sinking, which is the mountain sinks into the neutron stars. Okay, so now I will finally get to what exactly I've done, now that I introduced the problem. The idea of the main goal of my PhD was to take all of this formalism that was done in Newtonian mechanics and rewrite it to general relativity. It's a pain, but I did it. So again, you start from the first principles equations. It's lovely. GR is lovely, but translating is always difficult because in Newtonian people say mass, and then in GR you're like, okay, what mass? Rest mass, gravitational mass, and you have to solve all these problems. All right. So the first equations from first principles are rest mass conservation, conservation of the energy momentum. We have Einstein's equations that, given matter distribution, generates metric, and Maxwell's equations. And again, we can take and do all the similar approximations that we've done in Newtonian in the GR case. The first one that I did in Newtonian was that the mass of the mountain was much smaller than the mass of the neutron star itself. So the gravity was this Newtonian potential. We do the same thing. We fix a Schwarzschild spacetime for the same reason. We also assume that the fluid is a perfect conductor, so you don't have electric fields in the rest frame of the fluid. The system still evolves from quasi-static steps of equilibrium. So the forward velocity of your fluid is proportional to the time vector of your space. And we assume that the system is axisymmetric. What that means is that if you take any tense or anything that talks about the fluid, if you take the lead derivative with respect to the axisymmetric Killing vector, should be 0 for everything that you put here. Here put the Faraday tensor, but it could be the energy momentum tensor, anything. And then the magnetic field is poloidal. Again, Newtonian, remember that I had B here, now I have the Faraday tensor, but it's basically the same thing here. Phi is the coordinate along the azimuthal direction, and psi, again, is the function, the scalar field that generates the magnetic field. And by the way, it looks like I'm over-focusing on psi. What about density, pressure, and all these things? Because the system is in equilibrium, all these other quantities come from psi. So once you know the psi distribution, you can calculate the mass distribution, the pressure distribution. All right. So again, using all these conditions into the first principle equations, you get this equation here, which is the GR version of the Grad-Shafranov equation. And if you expand this in Schwarzschild spacetime, you get this. And this term here in red is the difference between the Newtonian and GR version of the problem. But overall, you see that it's similar. You also have a source function here on the right-hand side. And the source function is this. There's some differences here, but overall, the general form of the problem is well maintained when you go to GR. So, of course, you cannot, wait a second. So, of course, you cannot solve these things analytically. You need to go to numerical methods. And what is the numerical approach that we've done? We solved the Grad-Shafranov equation by successive over-relaxation. And the flux constraint is maintained through this kind of loop. So the general idea is that you start with a psi, which we choose the dipole of the neutron star. And then with that function, you calculate the source, so this f of psi. So you calculate the source. And when you calculate the source, you have the Grad-Shafranov equation. So you solve the Grad-Shafranov equation with SOR. Then Grad-Shafranov equation is going to give you a new psi function that you wonder relax, whatever that means. And you calculate a new mass flux constraint. And then you have a new Grad-Shafranov equation, and you keep doing this. So these are the quasi-static steps of equilibrium. So the Grad-Shafranov is an equilibrium equation, and you solve it, you get an equilibrium distribution. But then you put it into the flux, you get a new source, and you do this until the system relaxes to a final equilibrium. So when I say final, it's not time, the physical time, but it's final through this under relaxation iterations. But there is an analogy between the physical time and this method. All right. What do we get? We get that the system actually converges and finds an equilibrium. To run this for longer, it even stabilizes here. And this is a nice plot. This is one nice thing about working with GR and when you have the Newtonian solution is that, so this is a plot of the dipole moment, for example, and you have here the GR solution, the blue line. And right here you have the Newtonian solution, the brown line. If you go into your code and you artificially change the value of the speed of light, so you can say that instead of 3 times 10 to the 8 is 6 times 10 to the 8, and you keep doing this, what should happen? Your GR result should converge to your Newtonian result, right? If the speed of light was infinite, there would be no corrections. So this is exactly what we see, right? The solution converging. All right. And we get the same kind of qualitative pictures. You first start with a dipole, and the mountain deforms this magnetic field to create this deformed state here. This is the GR solution versus the initial dipole. And here I'm also plotting the GR versus Newtonian. So GR is the solid line and Newtonian is the dashed line. So what you can see is the GR solution is less deformed than the Newtonian solution. And just a disclaimer, this kind of plot, when you see it, be a bit suspicious of plotting Newtonian and GR solutions as the same thing. For example, altitude here. What do you mean by altitude? What reference frame? This is all the questions that you have to do when you're doing GR. So here I chose the reference frame of this neutron star itself at rest with respect to the neutron star. So this kind of comparisons are somewhat artificial, but you can talk to me later and I can discuss this with you. But anyways, you can get some invariants that show you that this is the picture of the distortion is less in GR than in Newtonian. This is also a comparison of the magnetic dipole moment up to R, difference Newtonian and GR again. So you see that in GR it stays a bit more like it was originally than the Newtonian case. And if you plot the actual magnetic dipole moment per accreted mass, you actually get this 3 times difference. So for you to screen the same amount of magnetic dipole moment in GR, you need 3 times more accreted mass. This is the density distribution that I was telling you about earlier. So it's a bit hard to see, but if you look carefully, so this is the GR. Yeah, the right-hand side is the GR solution, and the left-hand side is the Newtonian solution, density distribution. The GR one is a bit more compacted to the angular size, and is also not clear to see, but it was also more compacted in the radial direction. Okay, so now work in progress, some things that are happening. The Grad-Sharfanov method, it's limited by some stability conditions. When you start accreting mass, the magnetic field is going to deviate a bit, but when you increase a lot the mass that you accreted, the magnetic field lines is getting so distorted it reconnects, which is something very hot topic here in the IAG. So you start seeing these bubbles and this reconnection sites. So, and then the code crashes when this starts to happen. And this is the same Newtonian and in GR. So we say that from this point onward, the Grad-Sharfanov method does not work. So you are going to need to actually do some HD solvers to follow the evolution of the system. All right, these results and others were discussed in this paper. And now I will go to the continuous gravitational waves part. So keep the mountains, but before I go on, I just need to talk about continuous gravitational waves. Which, by the way, I don't like the name continuous, but okay. So continuous gravitational waves are gravitational waves with constant frequency. So the gravitational waves that we have observed so far in LIGO, they are bursts of some kind. You have in spirals, and then you see some gravitational wave emission, and it peaks at some point, and then it rings down, and it goes away, right? So transient. And continuous gravitational waves are not that. Continuous gravitational waves are gravitational waves that are emitted for a long time. In the light analogy would be like monochromatic or something. But I don't like the name continuous because in mathematics both are continuous. But anyway, so these are gravitational waves that can exist by general relativity, and can we actually observe them in the universe? For that, we need a candidate like sources. The best candidate of source is this massive stars rotating with non-axisymmetric components, meaning a neutron star with mountains, right? There are other exotic objects like some axion clouds, or you can see this as a binary evolution from very far away when they are like not changing a lot of the radial position. But anyways, I'm interested in the rotating star case. So you have this model called the triaxial model, where you have a star and it has its moments of inertia, and the quadrupole tensor of GR in this case here is just the moment of inertia term, tensor plus some constant terms. And for gravitational waves, you need the second derivative of the quadrupole moment. So this constant terms go away. So what actually matters is just the moment of inertia tensor. Again, when you take this and you run the math and do the GR stuff, you can calculate the amplitudes of these gravitational waves. And the amplitudes depend on these things right here. R is the distance to the observer, of course. This is the amplitude, so it goes with R. You have the ellipticity of the object, the frequency, and constants. The ellipticity is defined by in this case here, that it's rotating through this axis, is the difference of the moment of inertia in one of the principal axis divided by this moment of inertia through this principal axis here, that is the rotation one. Simply in an ellipsoid shape like this one, the moment of inertia, the ellipticity would be B minus A over A, where this B is semi-major axis, radius, and so on. Not exactly, there are some corrections here. This is the reason why I asked about geophysicists in the audience. I think in geophysics they call this flattening. I'm not too sure. And just to have an idea, again, that's why I was asking about geophysicists. What is the ellipticity of Earth, for example? The ellipticity of Earth is approximately this value from my Googling, so don't trust me 100% here. So it's 3.35 times 10 to the negative 3, right? If you are jumping the gun and thinking, wait, continuous gravitational waves from Earth, not a chance. The frequency is very small. Like we rotate in our axis in 1 day, and this kills the gravitational wave emission. Anyways, now let's go back to the mountains. So I did the simulations and I got the magnetic field lines and I got the density distribution. And now I can finally go and say, all right, what is the ellipticity value of my star? And then the ellipticity can be calculated this way. And this term here, I put it on purpose because this is something that people don't talk about very much and is very exciting theoretically, is that when we think about gravitational wave emission, we think about the mass quadrupole, but it's actually the mass energy quadrupole. If you had a pure magnetic dipole rotating outside of the axis, the magnetic axis, just the quadrupole, no mass, just the dipole moment, no mass, that would also emit gravitational waves because magnetic field also have energy. If it has energy, it has mass. So, so yes. So this is the two contributions. You have the rest mass energy contribution and the magnetic energy contribution. For the plasma people, this is very familiar, right? B squared over 2, sometimes B squared over 8 pi, the magnetic pressure. Right. But in our system, the mass part is the important part. Why? Because this is the ellipticity that is calculated from the mass values. So here I put the comparison between Newtonian and relativistic. This is an okay comparison. I told you that Newtonian and relativistic you should be aware. But this is an okay comparison because it's just invariance. You integrate over the whole space. So it's fine. So it's the ellipticity by the amount of mass accreted. So in the GR case, you get around 10% more. I should have asked this question. But you have 10% more ellipticity. And going back, looking at this, can you tell which one has the higher ellipticity? I already said that is the GR case, is because the mountain is more compressed in the angular direction, so you have a higher moment of inertia, so you have higher quadrupole, you have higher continuous gravitational energy. All right. And this is the magnetic field contribution. This is the magnetic field density, and this is the magnetic field contribution. Look at the scale here. Minus 11, the mass one was minus 5. So the contribution of the magnetic field is much lower. Right, and this is another comparison that I did. I vary the compactness of the system. There should be a star here, a star here. So if you vary the mass and the radius of the neutron star, you're varying the compactness factor. That in GR, this is what gives you the corrections. Here's in natural units, but there was a G. So when the compactness decreases, you should have the Newtonian, the relativistic results approaching naively. So here, fixed mass, varying radius. So when radius is bigger, compactness is smaller. So the solutions do approach each other. And now here, fixed radius, changing mass. If you decrease the mass, the solutions should converge. But you see that there is a not so simple behavior here. But remember that this is not like the speed of light test. The speed of light test is a great test because you're just varying the speed of light, and varying the speed of light to the Newtonian model changes nothing, but it changes everything in the GR model. So you have an independent test. But this compactness test is not so obvious because when you change the mass and the radius of the star, you're changing everything in your model. So, but anyways, it's plotted here. All right, so now for the exciting bit, at least for me, can we actually detect continuous gravitational waves? So far, okay, so this is my estimate of strain, continuous gravitational wave strains from magnetically confined mountains. So again, as I said, it depends on ellipticity, frequency, distance, moment of inertia. So if you take these things together and -6 here, you get 4.7 times 10 to the negative 26. If you are a gravitational wave person, and you don't study this, you might say, okay, we are never going to see this. But because the sensitivity of the instrument is orders of magnitude, it's higher than that, lower than that. But there is a crucial difference here. The continuous signal, you can take advantage that is always there to improve your statistics. Basically, you can take a part of your signal, translate it, put it on top of each other. If there is always a signal there. They should interfere. If you shift a little bit, you should find a way that your signal increases. And you can do some very clever F statistics, things that I don't understand, and improve the sensitivity of your detectors. And by the way, this is actually, I said that this is a small value, but this is probably an overestimation because my model is isothermal, very simple. To put more realistic equations of states, this number, I believe, should go down, like in the Newtonian case. And, right, so this is the paper about that. But yeah, so the emissions these are the estimates for the emissions. And theoretical and computational modeling is crucial. The same way with binary collisions of black holes. If you don't have a model to do the match filtering, here we don't do match filtering, but you don't detect. And searches for continuous gravitational waves happen all the time in the LIGO data, and so far they have not been detected. You can do a lot of different kinds of searches. You can do target searches. This is when you have a neutron star in the optical, a pulsar that you know the frequency, the localization, and you go and you do a target search. So high sensitivity, very low computational cost. You can do a narrowband search, which is you kind of know, and then you do give some interval for the frequency and position to change. So high sensitivity, a bit more computational cost. And then you can do director or blind. Blind is also known as all-sky searches. In all-sky searches, you just say, all right, here's the whole sky. We're going to look everywhere in the sky and everywhere in frequency. So these searches are very expensive computationally. In Germany, in the Albert Einstein Institute, they have even a citizen science thing that if you're not using your computer, you donate computational resources to the scientists, and then they access your computer and run simulations to try to find these gravitational waves. And again, it hasn't been detected in the LVK data. So this here is a paper that came out in August this year, so very recent, from the search. No, this is older. This is the 2023 one. So the Einstein at Home is the citizen scientist project, and the all-sky search for continuous gravitational waves. So it shows that they haven't detected, and they put some upper limits. This is the paper from this year from the Einstein telescope. So for those who are not from the area and doesn't know, the Einstein telescope is a third-generation detector of gravitational waves that is being planned to be built in Europe, and it's so it's a much more sensitive experiment, bigger and in maybe triangular configuration. And they released this paper, which is the science of the Einstein telescope. It has 900 pages. And here I pointed out there is gravitational waves from rotating neutron stars and continuous waves and long transients. What do they say about this problem? So a prime candidate for this emission of continuous gravitational waves would be Scorpius X1. And here is the integrated sensitivity of the Einstein telescope, the proposed sensitivity. Here is the two configurations that they are studying, 2L and triangular configuration. But anyways, and here in this band is pretty much like an upper limit kind of sorts. for emission of Scorpius X1 of continuous gravitational waves. So you see that it's in the detection zone of the instrument. Yeah, it is like some orders of magnitude depending on the frequency below. So we would assume that we can detect this object. And another nice plot that they've done is that one, which gives you distance, frequency, and these are ellipticities, the things that I was talking about. So for a given frequency and a given distance, if it's below this line, given frequency, distance, and ellipticity, if it's below the line, you detect it. So you see the 10 minus 8, it's here, 10 minus 4 is there. And this area here, this pink area, is the Milky Way. So we're not expecting extragalactic sources, we're expecting galactic sources. So we should observe, even if it's like 10 to the negative 8 ellipticity. And so the community is very positive about this. So both the theoretical models, including mine, say that detection is highly probable with this third generation detectors. And again, this animation, because I love it. So I just wanted to say that, like, the detection of continuous gravitational waves is going to be one of the next big milestones of the field. But for that, we are going to need third generation detectors. Einstein telescope, but also Cosmic Explorer in the US. But the US, who knows? Yeah, so I just want to finish my talk here with some future work. Again, as I said, I'm investigating this bit of reconnection in the mountains, but like other improvements can be done in generalizing the equation of state. This is a very important one that needs to be done. Consider other time-dependent effects, such as mount sinking, atomic diffusion. Analyze the stability and reconnection using GRMHD solvers like Athena, and consider the effects of Newton's star rotation in the curvature of spacetime. This should be a smaller effect. Yeah, so I would like to thank the department for inviting me to do the seminar, and all of you who have listened to the talk. Thank you. In time.
Thank you. We have time for questions.
Thank you for your talk. Many things new for me. Is it possible to detect some signature of these effects in the pulsar time variation?
Yeah, very good question. Of course, these mountains, they will affect not just gravitational waves, but also the other emissions of the neutron star. And yeah, you have observational signatures. I confess that I don't know much about those. But in the literature, there is like, well, there is the obvious one of the reduction of the magnetic dipole moment. That would be, but that's multi-factor, right? You have other factors decreasing the dipole moment. But yes, in the P dot diagram, you would also have other effects related to braking and so on.
More questions?
Okay, thank you for your talk. I have a question regarding your prediction for observing this guy. Have you thought about doing a population study of the possible system that would emit and contribute to the total signal?
Yeah, very good. Yeah, just saying one thing, the continuous gravitational waves and gravitational waves in general would allow you to detect more than we know, because for us to know a pulsar, it has to, the jet has to shine in our direction. But of course, there is some supernova remnants that you think there is a neutron star there. So in gravitational waves, you would be able to see those things. But yeah, population studies are definitely something that happens, and I haven't done it myself, but there is a lot of people in the literature who has done, which, by the way, the people from the Einstein telescope, there is a very nice plot that they give as well of like, these are the candidates that we know, these are the upper limits that we get from LIGO, this is how many we expect to observe with Einstein telescope. And it's like, we don't know, right, the parameters, it depends on the models and so on, but it could range from like tens of sources to hundreds of thousands of sources. So yeah, that's a very interesting thing. Thank you.
Thank you, Pedro, for a very nice talk. Can you explain what you mean by the variation in the speed of light? Because
relativist to relativist.
Yeah.
Do we have a? Let me go back all the way to. Not that bad. Okay. So the term in red, nice that I have the red pen as well. So you have the arm to m over arm dot side. So this is the term that appears in the Grad-Shafranov equation in GR that does not appear in the Newtonian version, right? Of course, as you know and you might expect, this is written in geometrized units. And if you actually write this in SI units, you're going to have 2G.
You are talking about the relativity is fine, but it's not supposed to change the speed of light.
Yeah, yes. Wait, no, but wait. Right, C square? Yeah. So I'm not saying that the speed of light changes.
Yeah, I'm just skeptical about because you used 1 or 2 times.
No, I'm not changing. I'm not saying that the speed of light changes through any things. It's just that this thing here has a number to it, right? This has a number, right? What happens if you artificially say this is not 3, this is 6? GR still works. It doesn't matter what is the number in what your system of measurements are. I'm just saying that if you take this number instead of 3 but 6 or 12, the quantifiable corrections are going to be different, right? If you're keeping mass, distance, everything the same, but you just take the value of the constant speed of light and change it. The relativistic effect gets smaller, right? Because of the C square. So you're killing, if you make it 2 times bigger, you're making the correction 4 times smaller. And that's all I mean by this test here. And you can see that is like quadratic in a way. So it's just changing this value. Not breaking relativity, not doing anything nasty, I promise. Any more questions?
Okay, the last one, okay?
Yeah, thank you, Pedro. Have you calculated the how many difference you have, for instance, in the case of the amplitude of the continuous gravitational waves compared to the black hole or neutron stars merger before the ring down? And have you also do you have an estimate for the amplitude that the space interferometer like LISA it will be able to observe?
Yeah. So the continuous waves from neutron stars, they are orders of magnitude lower than the binary mergers of black holes and black hole neutron star, neutron star, neutron star. So that is clear. So you have my estimates of 10 to the minus 26. I think I'm awful with remembering numbers, but I think the gravitational waves are minus 22, minus 23, something like that. Minus 21, yeah. So they are order of magnitudes lower. The problem with LISA, this is a question that I had also during my PhD. So you have Earth here, and you have the LISA satellite forming this. The problem is a problem of frequency band, and wavelength band. The neutron star rotates. This neutron stars in low mass X-ray binaries, they are called the millisecond pulsars because they run the periods milliseconds. So you need a Earth-sized detector, 10-kilometer detectors, because where did I put it? So this is the Einstein telescope predicted integrated sensitivity. So you see that it depends on the frequency here, right? So for very high frequencies is bad, and for very low frequencies worse. And the LISA band is like somewhere lower frequencies. So it's other kind of objects that we're going to see, supermassive black hole mergers and stuff like that, or a stochastic background maybe.
Okay, thank you.
Yep. Something like that. And this is, by the way, as I said, integrated in time, because the actual sensitivity of the Einstein telescope is already like here. So why am I showing it here? Is because, again, because of the continuous waves being a long-lasting signal. When you do the statistics and all, you improve the sensitivity up to these low levels here. So the LIGO detectors are way up high, but you can also consider the LIGO integrator sensitivity and would be a bit lower. And I think I have a plot of that. So this is a old plot, 2015. Maybe two, no, this is already Einstein telescope, and this is advanced LIGO. So it would, yeah, here's a comparison. Einstein telescope and LIGO, but again, integrated in time. It is, LIGO is 4 kilometers. Einstein telescope is 10. Well, they are right now, they are discussing what kind of detector they should build. There is a 15 kilometers one or a 10 kilometers one. 10 kilometers one would be triangular to get some advantage of this. Or they can build 2 L detectors of 15. So again, LIGO is 4, this is 10, 15. And Cosmic Explorer, it's 40, because the United States, it's big is better. No, okay. But yeah, but we are not too sure about Cosmic Explorer. Einstein telescope is more probable to be built. And in Europe, they are already like fighting to see where they're going to build, and in the United States, they are, what's going on? Are we going to shut down LIGO?
What are those vertical lines in the sensitivity curves? It also appears in the other plot, and I was curious.
Yes. That's a question for an instrumentalist, which I'm not. But these are noise, like very high noises coming from a particular thing. So, for example, do I know any particular noise? I think a geophysicist here would also help, like tectonical plates moving at a certain frequency. Yeah, seismic noise. There is something that they call Newtonian noise, that is density variations on Earth. Like, and there is a very cool plot from LIGO as well, that they have visits and they have people working on site every working day. And you can get from the detectors a 7-day cycle of like people walking near the detector and so on. So you have all these noises. But yeah, those are particular noises that they cannot eliminate. Yeah, Lisa wouldn't have any of those. Maybe some other, but none of those.
Okay, thank you again, Pedro.
Thank you.